13 microseconds. That was the size of an error that quietly escaped GPS on January 26, 2016, and spread across continents. 15 satellites broadcast the bad correction, pushing many thousands of GPS-controlled clocks roughly 13 microseconds away from official time for hours. Yet navigation kept working. The error struck timing receivers instead, exposing a second GPS service most people never notice until it misbehaves. Some synchronized broadcast and power measurement systems recorded problems, even though 13 microseconds is far shorter than any human can perceive. So, if trustworthy satellite signals vanished across an entire country, what would actually break first? Maps, aircraft, phones, banks, or electricity? Here, GPS goes dark means civilian receivers lose every trustworthy satellite navigation signal they normally combine, not only the American constellation. The honest answer is not a cinematic instant blackout. Different systems begin spending different kinds of backup the moment space goes silent. A related, sometimes more dangerous failure may arrive before any screen says signal lost, because GPS can also be made to lie. A GPS satellite never watches your phone and never sends it a personalized position. It simply broadcasts where it is and when. Your receiver compares timed patterns from several satellites, measuring travel delay at light speed to estimate distances called pseudo-ranges, each containing small errors. 1 microsecond of timing error becomes almost 300 meters of range error. 1 nanosecond still represents about 30 centimeters. 4 satellite measurements solve 4 unknowns. 3 position coordinates, and your receiver's clock offset. Their imperfect distance spheres reveal both answers together. Atomic clocks provide the stable rhythm, but each satellite clock still needs correction. Ground stations continually monitor the constellation and upload fresh data. Relativity would make an uncorrected satellite clock gain a net 38 microseconds per day, but engineers compensate before that difference becomes navigational error. Once the receiver solves its clock error, GPS has delivered something just as valuable as location: a common, precise definition of now. Within seconds, position-dependent receivers can lose or distrust their fix. Surveying, tracking, drone, ship and aircraft systems may flag a problem. Jamming usually produces an obvious loss. Spoofing imitates satellite signals, potentially persuading equipment that its position or time is still trustworthy. At Newark, investigators traced repeated interference with a GPS-based airport system to an illegal jammer inside a passing pickup truck. The jammer disrupted testing and calibration, not aircraft in flight, but it proved a tiny local transmitter could overpower signals arriving from orbit. In April 2024, interference prevented 2 Finnair aircraft from completing Tesh's GPS-dependent approach. Finnair then suspended the route for 1 month. Tartu reopened after a terrestrial approach was installed, demonstrating both the dependency and the value of a genuinely different backup. In the United States, specified commercial operators must retain non-GPS navigation capability, while radar and air traffic procedures provide additional resilience. Inertial systems can navigate without satellites after alignment, but their error grows with time. Crews must keep cross-checking against independent references. Position failures announce themselves quickly. Meanwhile, thousands of fixed antennas remain perfectly still, listening to GPS for an entirely different product: time. Many mobile radio systems use precise timing to coordinate transmissions, handovers, and shared spectrum. If neighboring sites drift apart, interference rises and capacity falls. Financial systems need traceable timestamps to reconstruct which order arrived first, preserve audit trails, and investigate manipulation across machines in different places. Exchanges can continue on independent timing backups and holdover. Only as those reserves weaken does agreement between distant records become harder. Power grid sensors sample voltage and current across enormous distances. Shared time lets operators align those readings and see one changing electrical system. Without reliable timestamps, measurements can appear out of sequence or show false phase differences, weakening fault location, monitoring, and some protection decisions. GPS loss does not automatically switch off the grid, but synchronized visibility and fault diagnostics deteriorate, forcing greater reliance on local measurements. A power industry report records bad GPS data and a cheap receiver contributing to the loss of two 500 kilovolt transmission lines. That report does not justify a national collapse story. It shows wrong time can produce consequences before missing time forces equipment and operators into caution. Every dependency has a clock nearby. The crucial question is what that clock does during silence, because most of them do not stop. When a GPS-disciplined clock loses reception, it enters holdover. Its local oscillator keeps ticking from the last correction it trusted. A cheap oscillator begins drifting sooner. Rubidium, cesium, careful temperature control, and better software can preserve useful synchronization much longer. In one NIST test, a rubidium clock stayed within 1 microsecond for roughly 73 hours. That result is an example, not a guarantee. One United States scenario study modeled wireless service remaining stable for 24 to 48 hours before uneven degradation in then-current mobile networks. No countrywide outage has tested that countdown. Some sites may struggle within hours. Well-equipped networks could conceal the loss for days or longer. Among telecom, finance and power, mobile telecommunications are the strongest candidate for early widespread degradation, but towers would not fail simultaneously. Data rates may fall, handovers can become less reliable, calls may drop, and capacity can shrink region by region over time. A receiver declaring signal lost activates procedures and backups. A receiver accepting convincing false time can silently pull connected equipment away from everyone else. That is what made the 13 microsecond incident revealing. GPS remained available, but some clocks trusted an incorrect correction and carried it downstream. So the first equipment to fail needs fresh position. The first hidden network to degrade has the weakest clock and least independent backup. In the first minute, navigation and tracking alarms multiply. Surveyors pause, fleet markers freeze, and some automated work reverts to slower methods. Aircraft crews cross-check inertial systems, radio aids, radar, and controllers. Operations continue, but routes slow, and safety margins become more conservative. Road traffic loses accurate routing and fleet coordination. Dispatchers can still use voice and maps, yet finding incidents and allocating responders takes longer. Over the next hours, timing sites enter holdover. The weakest drift beyond their limits, while stronger clocks remain apparently normal and quietly consume reserve. Grid operators lose some synchronized visibility, while exchanges protect chronology with backup clocks. Both continue, but uncertainty and manual work grow. After one day, degradation may appear at weaker telecom sites, while transport inefficiency, delayed routing, and emergency response costs accumulate across the region. A United Kingdom study published in 2023 estimated one nationwide day without satellite navigation at £1.42 billion. That was a scenario, not a measured bill. In its first day, emergency service and road transport disruption produced the largest projected losses. Across 7 days, maritime losses grew more prominent. The lesson is that resilience depends less on one replacement than on diverse, independent sources. There is no universal replacement for GPS. Different users need different mixtures of position, navigation, frequency, absolute time, coverage, and accuracy. Receivers combining several satellite constellations can survive a GPS-specific fault, but broad interference may reach multiple systems sharing similarly weak radio bands. Fixed infrastructure can receive time through fiber, terrestrial radio, network links, local atomic clocks, or dedicated systems designed with different failure modes. But fiber, radio, or network time adds little resilience if every path secretly traces back to the same satellite source. Resilient designs compare independent sources, flag impossible jumps, and can reject suspect data. First, operators must know which systems depend on satellite time. So what breaks first when GPS goes dark? Position-dependent tools notice immediately. Timing-dependent infrastructure begins a quieter race between drifting clocks. Its true miracle is not merely telling us where we are. GPS keeps distant machines agreeing on when the same moment happened. GPS made precision feel free and permanent. Next, we will ask how machines decide which clock deserves to be trusted.